In RISAFoundation, we now have the ability to design steel, concrete, and timber piles. We've had the ability to design pile caps, but now we've added pile design capabilities in version 10. I've drawn up what appears to be a concrete abutment for a bridge, and we're just going to add piles in it. To begin with, under our global model settings, you can see here are the pile design codes that RISA will reference. You can see there's steel and wood in different versions. So you can choose whichever one is applicable to your project. Next, we want to go in and open our pile definition spreadsheet. I've already defined a steel pile that we are going to use in this demonstration, and now we can add a concrete pile. I'll go ahead and leave this as a 12 by 12 rectangular pile, but of course, here's where you would go to add in the different dimension, and if you would decide to use circular instead of rectangular pile. We can also change this to 4,000 psi normal weight concrete strength. I've defined a 45-foot pile length. Again, this is dependent on your results and your soil parameters that you have from your geotechnical report. I've done a 12-inch embedment into the pile cap or into the abutment. And the shear capacity is a user input, and I'm just going to go ahead and leave it for 5 kips for each of the piles in this demonstration. Under the concrete pile rebar, you can see it references use design rule. So we'll open up the design rule spreadsheet to see what is in there. Under the pedestal and pile tab, I've defined the longitudinal bars as number 8s and the shear ties as number 4s. Of course, it's just as simple as going to the drop-down menu to change that if you would like to use a different bar size. Next, we need to list our soil parameters. Again, this comes out of the geotechnical report that you have for your project. I have a 2500 PSF bearing, allowable bearing for this project. Under the depth properties, it says custom. So once you click on that, the little red arrow pops up. You get your default soil depth properties. And here's all the different layers that you can enter in that will match whatever your geotechnical report says. You've got the depth of each layer, your unit weight of each layer, the skin friction, and the unit tip bearing for each layer. Now we're ready to add our piles. Here's the piles that we defined in the spreadsheet. If you get in here and you decide, oh, I want to add a third type of pile, you can just click on this button and add it straight here. So you do not have to go all the way back to the spreadsheet, or you can even start here if you would prefer to enter it this way instead of through the spreadsheet. So let's add our steel piles now. And just like all the other RISA programs, we can just copy it out. And now that we have that, we can add our concrete piles. Once we have all our piles in, we can now add the loading. We'll start with the dead load. We'll add 30 kips of dead load. The Y direction is the gravity direction. And all positive Y loads are downward. So you do not have to add a negative in front of it. The program does know that a positive 30 kips is 30 kips in the downward direction. Of course, if you had uplift, you would put the negative in. So we'll go ahead and we'll add 30 kips of dead load. And just to make things a little different, we can add just 15 kips to these back ones. We can also add some live loads. Also, to show how the program handles shear on our piles, we'll go ahead and add some wind load in the X and Z directions. You are also able to add moment if you do have moments that are acting on your piles. And just to kind of give you a look of what's going on, there's the isometric view. Now that we have everything defined and our loads put in, we can go to our load combination spreadsheet. I've already used the load combination generator to generate strength and service combinations for this project. And I just went to the load combination generator button and I generated the loads per the 2015 IBC, and I did strength and ASD for service. Of course, if this was a real bridge abutment, you would have to use the AASHTO code. And then we do not have the AASHTO code in, so you would just have to go in and manually input all of your factors for your load combinations. Now that the load combinations are in, we're ready to solve. So it's run. We can pull up our pile results, and you can see that it shows whether it's the steel or the concrete ones, the unity check in shear, and of course how much shear is actually in the pile themselves, and your soil unity check. Under the detail report is where we're going to get all of the information that we would need. So you've got your pile geometry, the material, the code used, the analysis and design results used to calculate the code checks. You can see under design results, you've got your pile capacity in compression and tension, and it also shows you the unity check and the compressive force that is happening on that pile. And your governing load combination if you wanted to go back and see which load combination governed your project. Here's your soil results, the shear check results, and then down at the bottom, you'll find the axial capacity diagram. This diagram shows the demand force in blue versus the static pile capacity, which is this red line. This diagram can be helpful in understanding the pile's load transfer behavior in the soil based on the total skin friction and ultimate bearing capacity of the pile. You also get a diagram of your pile and the different layers of the soil that you have designated. And that's for a steel pile. And of course, the concrete pile, you'll get something very similar. Here's a diagram of the pile itself, all the information of the pile, and you still get your design results for the pile capacity in tension and compression, your soil results, your shear checks. Here's your punching shear. That way you know the concrete that your pile is embedded into is strong enough and properly designed. And then here's your axial capacity diagram for the concrete pile.